Welcome to part 3 of ecosystem modeling and the century ecosystem model. So over the previous two lectures, we talked about general ecosystem modeling. Then we looked at the century and the descent models in more detail. And this lecture, we're going to look at some descent results for an agricultural system in the Great Plains and discuss the feedbacks between carbon and nitrogen cycling in managed agroecosystems. The basis for this lecture is a paper that I wrote with my colleagues in 2011. We used the descent model to evaluate the historical impact of land use changes on greenhouse gas emissions over a 120-year period starting in the late 1880s. So from the late 1880s to the present, European settlement of the Great Plains and the corresponding agricultural practices dramatically reduced soil carbon levels and increased greenhouse gas emissions. We used the historical evidence from land use change in the Great Plains and used the descent model to simulate the environmental consequences of converting grassland to agricultural crops. We simulated land use histories of 21 major counties in 10 different states in the Great Plains. If you take a look at this paper, you will see a map of the Great Plains and the 21 counties that we looked at. We simulated all the major crops that were relevant to each county. And the paper goes in detail about results from Hamilton, Nebraska, and I'm going to talk about that a little bit later in this lecture. And for your homework, you're going to be looking at a spreadsheet of results from Weld County that was also one of the counties that was simulated in this modeling exercise. The descent model outputs that were important to this study were crop yields and soil carbon levels and N2O emissions and methane oxidation. And also soil nitrogen mineralization. And we found that the initial cultivation of native grass caused the greatest amount of greenhouse gas losses over this whole 120-year period. And initially, greenhouse gas losses were from the loss of soil carbon, but as agriculture progressed and fertilizer became available, the soil carbon levels either stayed the same or started building again, and it was the N2O emissions that took over as the major greenhouse gas. So one of the things that we did to calibrate and validate the model was to take agricultural census data for major crop yields across the Great Plains and get the simulated values of these crop yields to look as similar as we could to the observations. So there's 10 graphs here, and these are the 10 crops that we chose to look at in the Great Plains, and dry land and irrigated wheat. Dry land means just rain-fed, it's not irrigated, whereas irrigated, there's an additional source of water added to the crop. Dryland corn and irrigated corn, dryland sorghum and irrigated sorghum, dryland hay and irrigated hay alfalfa, and dryland cotton and irrigated cotton. So not all of these crops were grown in all counties, but there were multiple counties that had these crops. And the thing to look at is that the 5-year moving average of the model, which is the lighter gray line, follows the trend of the observations, which is the darker black line. Another thing to notice is that yields generally increased over time. So starting from when crops were initially planted, yields were relatively low compared to what they were in 2003. And part of it is because farmers got better seed, they got crops that were more productive over time, and also when fertilizer became available around 1950, that substantially increased yields for most crops. This particular graph isn't from the Great Plains study, it's N2O emissions from Hermitage, Australia. But I just wanted to show you another example of day-cent output. So it's really wonderful to have any field site that has continuous N2O emissions data on a daily basis, because we can compare day by day N2O predicted by the day-cent model and N2O as was measured. And it's really, really difficult and challenging to get N2O good, and these are actually pretty darn good results for the day-cent model, even though some of the high points are off a little bit. But the timing of the N2O emissions that the day-cent model predicted in the blue circles coincide really well with the timing of the observed N2O fluxes, which are the orange dots. And this was also a challenging site because of the kind of soil which is pictured here. It was a soil that was really high in clay, and it has just a lot of unusual characteristics that don't make it like the average type of crop you might have here in the US. So we're going to focus a lot on what happens to soil carbon and N2O emissions when a native grassland is converted to agriculture. And on the right, you can see a grassland, and notice the root systems of these two systems. And the left is, I believe, a wheat. The root systems of a perennial grass, a native grass, are much denser, go really deep into the soil relative to the amount of roots that are in an agricultural crop, especially an annual crop. Another thing about annual crops is that the above ground biomass tends to be harvested each year, and so there's always some removal of above ground biomass from the system, whereas a native grassland, yeah, there might be some grazing, but then some of that biomass that's grazed is returned by the cattle as manure and urine. Here's just another example of the difference between a perennial crop in a grassland or a prairie plant and a annual crop like a corn. The root systems of the perennial plants just are very deep, and when those roots turn over, they contribute to soil carbon formation, and below ground material that gets incorporated into the soil is more likely and more effectively becomes soil organic matter than any kind of plant residue that's deposited on the surface, although plant residue on the surface can definitely contribute to soil organic matter formation. Okay, we're going to spend some time with this slide because I would like you to really understand all of the dynamics here. And the paper has these same figures in it. So if you want to look at the paper too to get a little bit more of a description about the results, you can look at the paper too. These results might be just a tiny bit different than the paper. I'm not sure. I know that the Weld County results that you have for your homework are just a tiny bit different than what's in the paper, but all of the dynamics are the same. So what we have here are 5 graphs. Total net greenhouse gas emissions over the whole 120-year period is the top graph. Soil carbon, above ground production, net nitrogen mineralization, and N2O emissions. So let's take a look at how all of these different output variables of the day-cent model change over time. So the green line is pasture, which is native grassland. So that's kind of the control here, is if you just left pasture alone, didn't manage it except for maybe some grazing of cattle or bison. There would be some interannual variability in these variables, but in general, the grassland would have relatively constant values for most of these variables. And then you can see then the other lines, like the orange line is dryland or rain-fed crops. So that's those began in about 1870, so that the native grassland was plowed out in 1870 and was plowed for a number of years after the initial date of plow out. Irrigation began at around 1950, and fertilization also began around 1950 for both dryland and irrigated crops. And the irrigated crop in this particular example the irrigation doesn't start till 1950. So the blue line is the irrigated corn, and so that doesn't exist before 1950. The other two lines, the Conservation Reserve Program and Return to Pasture after cropping, I'm not going to discuss them in much detail. I just really want you to understand how plowing out a native grassland and irrigating and fertilizing affects the dynamics that you see here. Let's start with soil carbon and look at it in more detail. So the green line is the native grassland. It goes up and down a little bit based on weather, but management's not changing much from year to year, so you just get a little bit of interannual variation. So then the soil carbon, though, look at how it plunges in the orange line. The dryland crop, the soil is disturbed, it's turned up, it's chopped up, and that continues for many years. And what that does is exposes that soil carbon to microbes, makes it vulnerable to decomposition. And what used to be soil carbon is released as CO2 in the atmosphere. And after 70 years of cultivation, before irrigation and fertilization start, that soil carbon has dropped to less than 50% of the original amount that was in the native grassland. But when fertilization begins, then the plants are a little bit more productive and there's more residue going into the soil. And you can see that after 1950, those lines start going up, especially for the irrigated crops, because they're even more productive because they're irrigated. Let's look at the above ground production graph now. So it seems to start off that the above ground production of the dryland crop is very similar to the above ground production of the native grassland, although the dryland crop does tend to drop a little bit below the productivity of the native grassland. Until fertilizer begins in about 1950, then the dryland crop above ground production increases, and at the same time with fertilizer and irrigation, the irrigated corn production also increases. Let's look at net nitrogen mineralization. So when soil carbon is destroyed, the carbon part of it goes into the atmosphere as CO2. The nitrogen part of that organic matter is mineralized, and so you see a boost in nitrogen mineralization at the same time that the soil organic matter is decreasing. But then the soil becomes depleted in carbon over time, and so that net nitrogen mineralization for the dryland crop drops quite a bit up to the point of around 1950. At 1950, because fertilizer is added, then net nitrogen mineralization goes up in the dryland crop and even more so in the irrigated crop. Because of the nitrogen mineralization, that boost in nitrogen mineralization at plow out, N2O emissions also go up. So you could see in the lower right graph, N2O emissions, the gold line shows a big increase in N2O emissions relative to the native prairie because of that increase in net nitrogen mineralization. And then it decreases, N2O emissions decrease over time. But then when fertilizer is applied in 1950, N2O emissions go up in both the dryland crop and even more so in the irrigated corn. And so the top graph summarizes all of the greenhouse gases. And so you could see in the very top graph, there's a huge spike in CO2 emissions. That spike is from CO2 emissions and maybe some from N2Os, and when the soil is initially plowed out. Then the greenhouse gases emissions get lower and get to almost zero by the time 1950 comes around. So in this particular graph, the negative value for net greenhouse gas emissions is desirable because it's from the perspective of the atmosphere. It's removing greenhouse gases from the atmosphere. So a negative value in this example is what we desire to see if we want to manage an ecosystem for reducing greenhouse gases. And then finally, in the top graph around 1950, there's soil carbon building, so that's going to reduce greenhouse gases. That's going to remove greenhouse gases from the atmosphere and put it into the soil. So that's going to make the greenhouse gases more negative. So the agriculture or the irrigated crops seem to be able to sequester greenhouse gases to a degree, whereas the dryland crop was kind of bordering on neutral greenhouse gas emissions from 1950 on. So just to summarize a lot of the things that I just said in this previous example, soil disturbance from cultivation accelerates decomposition, soil organic matter decomposition. And decomposition of soil organic matter leads to increased nitrogen mineralization and increase in inorganic nitrogen going into the soil. N2O production increases when inorganic N increases in the soil. So inorganic N can increase in the soil when mineralization increases, or from nitrogen fertilizer, or from atmospheric deposition. And the N2O increase is especially noticeable when the plants can't use up all the extra nitrogen that's put into the soil. If there's an excess of nitrogen that plants can't use, then there's likely to be N2O emissions. Increased plant residue inputs increase soil organic matter formation. And of course, the opposite is true. Decreased residue decreases soil organic matter formation. Below ground plant litter inputs increase soil organic matter formation more effectively than above ground litter inputs do. And that's why the native grasslands can build up so much soil carbon when those deep roots turn over. A large proportion of biomass in perennial grasses is below ground, but in annual crop systems, the greater proportion of biomass is above ground, and much of that above ground biomass is removed through harvest. And the same temperature and moisture conditions that promote plant growth may also promote soil organic matter decomposition and N2O emissions. Nitrogen inputs stimulate both plant growth and N2O emissions. So you can see that sometimes there's a balance between gaining carbon and losing carbon. So nitrogen fertilizer allows you to possibly gain soil organic matter, but then the N2O emissions associated with that increase in fertilizer can increase N2O emissions. So that's it for part 3, and I'll see you in part 4.